Alrighty, so let's get started today with some more math. We're doing conversions now that use more than just the molar mass. Okay, so 1 mole. That is not only 6.022 times 10 to the 23rd atoms, but don't forget that could also be 6.022 times 10 to the 23rd molecules. These are different, and I will bring up that example during notes today. And so the new thing that we're learning about the mole is that Avogadro hypothesized, okay, well, 1 mole of a substance will occupy 22.4 liters. And so he put a condition that this has to be at standard temperature and pressure. Always assume that. I'm not going to give you a problem that doesn't have standard temperature and pressure. So if you have a volume, you can use 22.4. And so these relationships that I'm giving you, they can be used as conversion factors. So if I tell you 1 mole is equal to 22.4 liters, you can write your conversion factor as 1 mole over 22.4 liters, or the other way around, 22.4 liters over 1 mole. Shut up, Michael. Told me to plug it in. I was hoping you were laughing. I didn't see you laughing. I was like, I'm kidding. Okay. So I love to break things down visually. And I think this is a nice representation of the conversions that we're going to learn and the tools you will have. What is in the middle of all of this mess? The mole. Okay, the mole. And so always convert to moles before you go somewhere else. All right, that's going to be our buddy. And so it's so cute. I don't think they're actually this cute in real life, but someone went off on a tangent asking if mole and bull is the same thing. I have no idea, but so always convert to moles. Okay, now we're going to talk about what are those conversions. So what's the new conversion we just learned between volume and moles? Exactly, you're going to get used to that. 1 mole is equal to 22.4 liters. So that's our conversion, going from moles to volume, volume to moles. What about number of particles in moles? Exactly, Avogadro's number. And then what's going to give us the conversion between moles and mass we talked about yesterday? What was it? What did we use using the periodic table? We use the atomic mass to calculate the molar mass. So the molar mass is what we use to convert between moles and mass. And so let's do some math, right? Oh, wait, hold on. Got to teach you strategies first. So we talked a little bit about, what goes on the bottom, what goes on the top, but I like to visually represent this with generic letters. I think it's another way to look at it. So if you're just doing a one-step conversion, let's say you start with arbitrary units A. In your conversion, oh my goodness, what was that word? In your conversion fraction, you're going to put units of A on the bottom. And whatever you're going for, whatever the question's asking, we'll call it units B on the top, and that will give you answers in unit B. Now, when we do a two-step conversion, we'll start with our quantity A. We're going to still convert to some quantity B, but then we're going to say, okay, our final answer is actually quantity C. So we're going to go from B to C, and our answer will be C. So A to B to C in some sort of fashion as such. That will be like our conversion path. What do you think letter B's units will always be? Moles. Oh, I won't do an arrow. So this is going to be the generic outline of our problems. Okay, so doing just a couple practice problems using molar volume calculations. It's asking how many moles, so that's probably going to be our B, are present in 45 liters, or A. So remember, our setup is going to be A times B over A is equal to units of B. Some setup like this. Or another way I talked about yesterday, start with what you know, 45 liters, which means we have to put liters on the bottom of the fraction and moles on the top. What's our conversion between moles and liters? 22.4. Gonna know these real well. Oh, 1 moles, that doesn't make sense. Okay. If we calculate that out, we get 2.01 moles of N2. Any questions on the initial one? Okay, let's do moles to liters then. So moles is our A, because that's what we know. We have 14.3 moles of helium. And we want to go to volume. So we have mole on the bottom. I'm going to erase this so it's not confusing. Liters on top. 1 mole, 22.4 liters. So then we have 14.3 times 22.4. We get 320 with a dot because we need to make sure to have 3 sig figs liters of helium. Alrighty. Okay, so now we're going to move on to figuring out the numbers of particles. And so this is going to heavily rely on Avogadro's number. Okay, so how many moles contain this many molecules? So if we start with 1.806 times 10 to the 24th. And so I abbreviate molecules MOLEC, but I also understand that that can get confusing with moles, especially with my cursive S's. So if you ever need me to clarify, just let me know. And so we're going to go from molecules to moles. And in 1 mole, we have our 6.022 times 10 to the 23rd molecules. So dividing one by the other, we get 3.000 moles of HCl. So remember, my sig figs are based off of my initial starting number. The conversion factors do not affect my sig figs. All right, and then how many molecules of barium fluoride are there in 5 moles of it? So 5 moles we are going to convert from moles to molecules. So for every 1 mole on the bottom, 6.022 times 10 to the 23rd on the top, you would get 3.01 times 10 to the 24th molecules. Okay. So what I've been talking about, we haven't done yet, we'll do it now, but you can be asked to find the number of atoms from the number of molecules. So if we have 3.01 times 10 to the 23rd molecules of hydrochloric acid, we know that we want to get rid of molecules, so that will be on the bottom. We want to know how many atoms are in one molecule. So our one goes with molecule. So in one molecule of HCl, how many atoms are in it? Atoms. What's your inventory? We have how many hydrogens? 1. And how many chlorines? 1. So there's 2 atoms per molecule. So all we're doing is multiplying this number by 2. 6.02 times 10 to the 23rd atoms. Okay, that one's not so bad. You just got to be able to count how many are in the molecular formula. How are we feeling about the one-steppers? Who's ready to show off their two-stepping? I cannot two-step to save my life. Oh my goodness. Don't ever, I can never move to Texas. All right. So always convert to moles first. Moles are guy. And so there's a couple things here. Besides always converting to moles first, it's best that you do all your conversions in one line. So instead of doing like one conversion and then like starting another line and like doing one calculation and starting another one, the reason why this isn't best practice is because you can round your answer before you're done with the problem, and then therefore you'll end up getting the wrong answer. So do it all in one line, multiply and divide in your calculator all in one line, or just make sure you're not prematurely rounding. So we'll start with this problem here. So this is where the A to B to C, I think, comes in handy. We know that our B is going to be our moles. What's our A in this problem? Liters. We start with 1.12 liters and ask how many grams. So that's what we're solving for. And so looking at the relationship, what do we use to convert between liters and moles? We use our 22.4. What do we use to convert between moles and grams? Molar mass. So how we'll set up this problem then, start with 1.12 liters. We are going to multiply that by going from liters to moles, following our A to B to C track. And we're going to use our 22.4. The 22.4 goes with liters per mole. And now we're going to set up our second conversion fraction, where we're going to go then from moles to grams. And so we have to calculate the molar mass of CO2. So the molar mass of CO2 is going to be equal, what is the mass of one carbon? 12. Thank you. And then what is the mass of one oxygen? 16.0. And so we're multiplying that by 2 because we have 2 of them. So our molar mass is going to be equal to 44.0 grams. So we are going to use, or sorry, grams per mole. We're going to use that in our fraction. So we have 44.0 over 1. And so now we're going to take 1.12, divide that by 22.4, multiply that by 44, and we get 2.20 grams of carbon dioxide. How are we feeling about that? Keeping up with me, Sonny? All right. How many molecules of CO2 occupy 44.8 liters? So if I set up my calculation here, A is going to be liters, B is always going to be moles, and C is going to be molecules. And so if we start with 44.8 liters, we know we are going to want to go from liters to moles. And so we use our lucky number, 22.4. One of them, we got a couple here. 22.4 liters per 1 mole. And then we're going from moles to molecules. I'm gonna move this up. And that is 1 mole, 6.022 times 10 to the 23rd. Put that all in your calculator, you get 1.20 times 10 to the 24th molecules. And so I do also want to point out, when you are doing conversions with powers of 10 and you're putting that on your calculator, it is super important to put parentheses around both the coefficient and the power of 10, or else your calculator gets really sad. So make sure you're putting parentheses around both of these while you're putting them in your calculator. Oh, I forgot to erase this page. No peeking, I'm just kidding. All right. How much volume does 51 grams of ammonia occupy? So we are going from grams to moles to liters. So 51.0 grams, we're going grams to moles. So we need to know the molar mass of ammonia. Well, we calculate that. Ammonia weighs 14.0. We have 1 of them. We're going to add that to 3 times 1.0 for hydrogen. We get 17 grams per mole. So now using that, if we have 17 grams per 1 mole, we then are left to go from moles to liters. So 1 mole is 22.4 liters. With your calculator, you would get 67.2 liters of ammonia. Okay. Now, how much volume will 3.01 times 10 to the 23rd molecules occupy? So starting with that many molecules, we are going to go from molecules to moles using Avogadro's number. And then we are lastly going from moles to liters for 22.4 liters per 1 mole. We are going to get 11.2 liters of ammonia. All right, and lastly, one more. We are going to start with 3.01 times 10 to the 23rd molecules again. This time we're going to convert to grams at the end instead of volume. And so we're again using Avogadro's number to convert to moles. But then we are going from moles to grams, and we already calculated ammonia's molar mass up above. So I'm just going to use that again. And that gives us 8.50 grams.